Hello everyone, my name is Rishabh Behel and welcome to the lecture 3 where we are going to talk about retrieval augmented generation. I just want to clarify one thing here that the concept of retrieval augmented generation is not associated with the LangChain library. It is something associated with the large language models itself. So RAG is something that is associated with large language models and it can be implemented in many different ways, but we are going to use the LangChain library. Now, before implementing, let's first see what exactly is retrieval augmented generation and why do we even need it. We know that large language models are trained on a lot of data from all over the internet by the companies like Meta and OpenAI. This data is called pre-trained data. Until now, all our interaction with large language models has been with pre-trained data only. There are various problems with the pre-trained data. First of all, it is outdated. It has information till the date it has been trained. Secondly, they don't have access to your private data. Thirdly, no accountability. It gives us answers, but it can't tell where this information to answer the question has been taken. In retrieval augmented generation, we do provide an external vector data source which allows the large language models to generate answers which are reliable, real time, and domain specific. Now we are going to take some of our private data which we keep in form of PDFs, Word documents, PowerPoint presentations, Excel, Notion documents, etc. and ingest it into a vector database. For simplicity, I'm just going to take an example of a PDF. We will extract its content and then store it in a vector database. But once the content of a PDF is stored in vector database, if we query the large language model now, LLM, instead of generating a response back, it will retrieve data and context from vector database. Then together with query and retrieve data and context, it will generate a response. But things are not that simple while ingesting the data. There are multiple steps involved. The first step is to load the text from the document. Secondly, we need to split the extracted text into smaller chunks. How do you split the text affects how well retrieval works in your RAG pipeline. After chunking, we will create embeddings. Embeddings refer to process of converting data into numerical vectors that captures the semantic meaning of the chunks. Now finally, we will save original content of the chunks along with its embeddings and respective metadata into the vector store or vector database. Now when a user queries the large language model, it will first find the chunks with the help of a vector search which are closely related to the semantic meaning of the query. Now using the content of these retrieved chunks, LLM will generate a response for us. Also, the metadata from the retrieved chunks will help us with referencing from where the response has been generated. So basically, the complete RAG pipeline is divided into three main sections. The first one is ingestion. So basically, having our private data and then converting it into different chunks and embeddings and storing it into a vector database. Then if the user asks a query, then we go to the second process, which is of retrieval through similarity search from the vector database. And finally, once we have the retrieved chunks, we are going to generate a response. And the third process will be of generation with the help of the retrieved context as well as the original query. When I was a high school student, I was given a question from my history book. Since I was not thorough with my history book, I couldn't even locate where this topic was mentioned in my book, which chapter or which page. I searched the internet, find the article on Wikipedia, and gave the answer. In today's time, I might have used ChatGPT, but teacher could and did tell the difference between the answer generated from internet or ChatGPT and the answer written by a student who has thoroughly read the book. That's exactly what we are going to solve today with the help of RAG. I'm going to ingest my history book into a vector database, and then we are going to ask questions from the RAG pipeline. These questions will be similar to the questions that were used to be asked by the teachers. Our RAG pipeline will not only generate response based on the textbook, but will also give references where exactly this content has been mentioned in the textbook. Now I have my history book here. My history book is divided into 5 different sections, and each section represents one PDF. So for simplicity, let's consider that we have 5 different books of history, and these are for my 10th standard. Now let's go to the Google Colab. So I have the basic structure made here. I have divided the complete notebook basically into 3 major sections. One is the ingestion, where we take the PDFs and extract the data, split, embed, and store in the vector database. Then the second one is the retrieval. So once we have the query, we are going to retrieve the context from this vector database. And finally, the generation, where we combine the context that we retrieved as well as the original query, and then pass it to the large language model to generate the response. First of all, I'm going to define the query. So I have this query where we are asking who was this specific person. Secondly, we move to the environment setup. I'm going to install the required libraries. Once the libraries are installed, I'm going to specify the OpenAI API key and define the model. Once the environment has been set up, I'm going to move to the ingestion part. In the ingestion part, the first step we are going to do is load the documents from the PDFs. Now, for the PDFs, if I have a section here and I have uploaded all the 5 files over here, you can do the same by clicking this option, selecting the files from your directory and uploading them. And after that, I'm going to write this code. So I'm going to first show you with a single document, and then we are going to combine the steps so that we can very conveniently do this for the rest of the 4 PDFs as well. So here I have imported PyPDF loader from the LangChain community library. And after that, I retrieve the docs out of it. And eventually I'm going to print the length of the docs, that how many documents I have retrieved from this specific PDF. And we are going to print that. And here you go. So you have this document object which is provided or defined in the LangChain library, and it has the metadata as well as the page content. These are the 2 different values that comes with the document object. And if you see, I have 28 total documents that has been generated. And if you see, this PDF itself has 28 different pages. For each page, it has generated 1 document. And if you see the first page here, the page 0 with index 0, the page content is something like this. And if I happen to take you here, you will see this text has been retrieved and all the images has been discarded. And then the text 2024 and 25 has also been taken, and section 1 has also been taken. So if you come to the first document here and you see the page content, you will see events and processes, section 1, 2024 and 25. And then we go to the second page, and second page has the retrieved context or retrieved content as 2024 and 25. So basically we have loaded all the text data from the PDF. I'm going to hide this. The second step after loading the document is splitting the document into smaller number of chunks. Here I'm extracting recursive character text splitter. So I'm going to divide the loaded text into number of characters. So I'm going to create chunks of 1000 characters each, where the first 200 characters are going to overlap. Also, I'm mentioning add start index as true, which basically means when I'm chunking the documents, it is going to contain a metadata field where it contains the original PDF, name of the PDF, as well as which page number was it, and also it will contain information like from which index the chunk has been generated. And I'm going to save all of this into a variable called all splits, which we are going to use later. Total of 81 different chunks have been generated from 28 different documents that we initially saw. So I'm going to print one of the splits here so that you can see how a split looks like, or one of the chunk looks like. And this is one of the chunk which contains the document object as per the LangChain. It has the metadata, it has the page number as well as the start index. And we were able to extract this information because of add start index equal to true. And then it has the page content where we have thousand characters. I'm going to print another document. So since I have printed two consecutive chunks, if you see, there's some kind of repetition. So the last 200 characters of the initial split has been repeated in the consecutive chunk because we set the chunk overlap as 200. So if you look, if you try to look closely, there's a bastion until mains has this specific line has been repeated here, where starts here and ends here. So this has been an overlap of 200 characters. Once we have created the splits and we see that they are working fine, I'm going to delete these and I'm going to work on embeddings. I'm going to import the OpenAI embeddings and I'm going to define a model for that. I'm going to use text embedding 3 large and we can run the embeddings. And once the embeddings has been generated, we can see how embeddings looks like. And what I'm going to do, I'm going to embed one of the chunks here. So if I print this, it will basically take the split number 10 and it's going to print its page content. This is how the text looks like. And I'm taking the same chunk and try to create embedding for it. And I want to show you how embeddings exactly looks like. And these are the embeddings that we got. So it is basically vector or numerical representation of the text that was printed initially. So it's basically numerical representation of the text, this text over here, which are called embeddings. We don't really need this, so I'm going to delete it for now. And once we also have embeddings, I'm going to move to the vector store. So for this example, we are going to use the ChromaDB, which is a vector store. I'm going to install LangChain Chroma. Once the LangChain Chroma has been installed, I'm going to import it, a Chroma object, and I'm going to define the embedding functions here. Once that's done, and we have to find the vector store, I'm going to add the documents, which is basically all the splits variable that we defined initially. It's an array or a list, and I'm going to add those documents to the vector store. And this was for the first PDF only. We need to repeat the steps for second, third, fourth, and fifth PDF. Now I did this in different steps because I wanted to show you how each step is working, from loading the documents to splitting and embedding. But we can combine these steps so that we can conveniently do the same for PDF number 302, 3, 4, and 5. So for that, I'm going to first install everything again. And basically I have defined the PDFs here. I can say and once done, I have basically extracted text from all the 5 PDFs and stored it into the vector database after splitting and embedding. So basically let's move to the next part of retrieval, where we're going to retrieve the context based on the given query. So the query, we have defined it on the top, who was this particular man, right? And I'm going to work with retrieval now. I am going to query the vector store that we defined initially. Now to work with retrieval, I'm going to query the vector store with the original query that we defined initially. And let's see what we got as results. Okay, perfect. So we got a list of document objects. So we have total of actually 4 documents. So 1, 2, 3, and 4. It contains the metadata, page number, source, and start index, and it also contains the page content. Now, by default, when we do the similarity search, it always gives you 4 documents by default, and you can change that and you can say k is equal to 6 for example, which defines the number of documents you want to retrieve based on the similarity search. And if I do this again, this time I got a total of 6 documents instead of 4. One thing you need to understand whenever you are using similarity search and you're defining k equal to 6, or if you're not defining k and it's by default 4, the algorithm, the vector store similarity search algorithm, is forced to find you 4 or the number of documents that you define from the context. And even if you are mentioning a query which has nothing to do with the text that you have or the content that you have, which is not related to the context at all, even then it is forced to find the documents which are closest as per the semantic search or the similarity search algorithm. So it will be forced to send you something. So anytime you have a query, you will always have the documents, but all the documents are not relevant all the time. If you give a query which is not related to the document or the PDF that we have ingested, then also you will get a response which is not in our favor. And if we ask the large language model to generate a response based on these documents, it might not make sense. So instead of using the similarity search algorithm or similarity search method, we are going to use another method which is called similarity search with relevant scores. It basically means that we are going to still get the documents, but this time along with the documents we are going to get a scoring that how close this document is to the original query. And once I run this, and you can see there I got the similarity search, it says 0.65. The closer this number is to the 1, the much closer the retrieve context is to the original query. Now let's change the query and take a query which is totally not related to the history book or the content in the history book at all. So let's go on the top, and instead of adding this query, COVID-19 has nothing to do with my history book. It's an old book. It doesn't contain anything related to COVID-19 that I know for sure. So I'm going to take this query, I'm going to run this. We have already ingested everything and we are going to do the retrieval here. You see, I still got 6 documents, but let's see what's the score that I got. Here I'm getting negative 0.07. It has the content, events, and processes, which has nothing to do with COVID-19, but still I got this document and has a very low relevance score. But it's our duty to understand whether these documents are relevant to the query or not. In order to filter the documents which are relevant and discard the documents which are not relevant to the original query, we're going to use something called score threshold. And I'm going to define the score threshold to be 0.3 in my case. And if I run this, I get 0 documents out. So basically similarity search gave out 6 documents, but they got filtered out. So all the documents which has a relevance score of less than 0.3 has been discarded. Now let's go up and let's get back to the original query, right? And I'm going to run this. And now again, I got some documents. And if you see the relevance score, all of the relevance score has been more than 0.3. And that's why they show up here. So I have total of 1, 2, 3, 4, and 5 documents when I was supposed to get 6 documents. To make this thing even more clear, let's set threshold to be 0.4. And according to this, even these this last one, the last 2 documents should also be discarded, and I should get only the first or top 3 documents. So I hope I was able to explain to you how this similarity search works and how do we need to filter the documents that make sense to our query and discard those which are far away or which doesn't make sense to our query. Now, once we are done with the retrieval, I am just going to print the documents that make relevance in a clear format. After that, let's move to the generation part. So I'm going to define 2 variables here. One is the context. So basically it's going to combine the page content of all of these 3 documents, and metadata is going to combine the metadata of the top 3 documents. I'm going to run this. And once done, I am going to define a prompt template to do the retrieval augmented generation, the final prompt template, which is going to query the large language model based on the content and the original query. Here in the prompt template, we are saying answer the given query, where query is a variable here based on given context, and context is also a variable here. We are also saying do not hallucinate or generate answers based on pre-trained data. If you can't find answer based on given context, simply say I don't know because I can't find any relevant context. And finally, we do have prompt here. We are going to invoke the prompt and passing in the original query as well as the context. So context it gets from here, and query we have defined on the top. And once we have invoked the model, we generate the response, and let's see how it works. Okay, perfect. So here is the generated response. You can see that. And at the end, I'm also printing the metadata. So basically referencing which page number of which PDF this content has been taken from. So basically you can point it out in the book where this thing has been mentioned. PDF 1, page number 11. It says page number 11. Basically, it's going to be page number 12 here because the index in Python starts from 0. And I'm going to find this name. So it is mentioned on the page number 12 and it justifies this. So I hope I was able to explain to you how retrieval augmented generation works here. But let's make it a little bit more simple. So I'm going to combine retrieval and generation now together so that it's more convenient. I did this separately here so that I was able to explain to you and make it clear to you how retrieval and generation works. I have combined retrieval and generation here together so that we can query here the original question and then based on that extract the data or extract the response. And I have changed the query here. I'm asking now about the Gutenberg press, and let's run this. And here we have generated the response, and this time if you see, it defines the fifth PDF here and it shows the start index as well as the page number. So you have page number 6 here which says Gutenberg and printing press. And that's all for retrieval augmented generation. I am going to put a link of this notebook down in the description of the video. Thank you.